Thank you, Graham, for your kind introductions. It's my great pleasure to be here. Particularly, I'm quite happy to talk my recent work in front of you. Particularly, you are so young. So young generation can develop a new type of solid catalyst, which can help us the future. So this is my lecture title. Where is the Sorry, the title I put in this slide is too long, but this is just my message to young generations. I think the catalytic crystallization is going to be very more important in our future catalysis development. The catalytic crystallization is not a new concept. It's rather old. But still, we have a lot of problems in crystallizations of a solid state catalyst. Usually, we used very much conventional synthetic methods like cold precipitations or impregnations or something like that. In this process, it's so convenient, but you know there are so many unknown phenomena taking place during the preparations. Therefore, you have always have difficulties in understanding the catalysis in such a complicated materials. To avoid this kind of difficulties, one of the best way is to make a crystalline solid where you have uniformity and so these kind of things help us to understand the catalysis more easily. So my talk is going to be divided in two topics. One is for ammonium SCl reactions, which can be catalyzed by the supported tungsten vanadium oxide, which is, again, prepared by simple cold precipitation and impregnation, something like that. But quite recently, we have found that this catalyst having a crystal structure shows quite high activity for this. The second topic is the sulfated zirconium oxide, which is a very old catalyst. This was born in 1970, something like that, such a long time ago. But still, industry used these materials. Again, this material was synthesized by a precipitation and impregnation method. Very recently, we have discovered this materials, zirconium sulfate, which is in a crystal form. This is extremely high activity compared to the conventional one. I want to talk about the topics one by one. In industrial catalyst for ammonia SCl reactions, the composition is tungsten and titanium, vanadium, but these are simply supported on the titanium oxide. That's why it is hard to understand the real catalysis over this catalyst. Very recently, my research group is focusing on the synthesizing the crystalline solid, particularly the oxide based on group 4, 5, and 6 elements. All those elements can possess the octahedral coordinations. We're also focusing on the material synthesis to form porous materials where you can expect some catalysis inside. So this kind of situation is very much important to obtain the high performance catalyst. Today, I just focus on these materials because these materials contain tungsten and vanadium in structures. The structure looks like this. You can see there are a cubic unit of tungsten oxide. These are combined together by one of the species in this form. Then eventually you have a pore in this case. In this case, the pore size is 5 angstrom. The preparation process is quite simple, as you can see here. Just you can dissolve the tungsten oxide in the basic solutions. Then you can obtain the monomeric tungsten oxyanion species in solutions. Then you can add sulfuric acid to get acidic solution. Then under the acidic conditions, monomeric octahedra are going to aggregate to form Cuban species in the solutions. Then we add the vanadium sulfate, which is a cationic species. On the other hand, Cuban is an ionic species. So that two species can react together to form such kind of species in solution. Then after adding an ammonia, which play as a role of, structure directed agent, then we can start hydrothermal synthesis at this temperature for 24 hours. Then you can obtain three-dimensional solid, which have porous structures. The structure is like this. I don't want to go to the detail. And from these kind of informations, we can confirm that the formation process that is shown in here. First, Cuban unit, then react with the vanadium zinc, and then forming this one. This species has been already reported in the literature, which is the simple soluble inorganic complex materials. But after applying the hydrothermal conditions, this species react together to form three-dimensional solid with the micropore. This material has a very much similar topology to zeolite A. Our material is cubic, and this one also cubic. The pore size is a bit larger than the zeolite, so that the void volume is slightly larger than the LT zeolite. Actually, this material shows high absorption properties of the nitrogen, showing that the is about more than 300. If you introduce the heavy element, large cations inside the pore, something like a cesium, then the surface areas sharply go down because the cesium just blocked pore. This material shows molecular sieving effect. The small sized organic molecules like ethane and methane can easily go through the pore, but the large size molecules like isobutane doesn't go into, so that this material can show the molecule sieve performance. So the small molecules like NO or ammonia, of course, can easily go through. So you can expect performance for the ammonia SCR reactions. Before going that, I have to show some catalytic properties of these materials. We conducted the analysis of the structure of a vanadium species by using this analysis. Then this kind of analysis supports that the vanadium species had a square pyramidal coordinations just between two Cuban molybdenum tungsten oxide. Acidic property, we conducted ammonia absorptions in the FTI analysis of this salt species. Then you can see Lewis acidity as well as Brensted acidities in this material. So we can assume that the Lewis acidities comes from the square pyramidal vanadium species where you have a vacancy in this. So therefore it can play as a role of Lewis site. Brensted site, Cuban unit has the negative charge. Normally these are neutralized by the existence of ammonium cations. But some ammonium cation can be removed under the treatment of acidic condition, leaving a proton. The proton may locate near Cuban unit. So the material can possess the Lewis acidity, Brensted acidity, and redox properties due to the vanadium and the coordinative unsaturated state here. So that this such a structure material can already possess such catalytic functions. So in this case, I have to remind you the material doesn't need to be activated by high temperature treatment. This material directly shows catalytic activities. In fact, we use these materials for ammonia associated reactions. The data is shown here. These materials show much high activity working at low working temperature. If you compare to the industrial type catalyst, which is supported on titania, well, it's good catalyst, but our catalyst is much superior than this. But very unfortunately, the material shows the decrease of the activity when you apply higher reaction temperature. In other words, material is not highly strong against the heat temperature. That's the pity things. Material is quite nice, but it's very unstable. That thing happens in many cases, but we need to overcome. We have to stabilize this material. How can we do this? We have been thinking of many days how to improve the thermal stabilities. I was not able to get a clear answer to it. But one day I got ideas. That's very simple. Industrial catalysts always use titanium oxide. Why titanium oxide? There's no reason why I don't have any clear answer to this. But titanium might have some stabilization effect on the surface complex. So I tried to introduce the titanium into these materials by doing such a way, which is very simple, but I don't want to go to the detail. But just after acid treatment, you can remove some of the vanadium from here to form vacancy, vanadium vacancy. This vacancy can be supplied with the existing titanium or zirconium cationic species. Then you can get these materials. The strange thing is that we can only remove the one vanadium, and we can only introduce one titanium or zirconium. There must be something tricky things going on in these systems, but nevertheless, it works, and we can get very stable structures, and even the microporosity enhanced because we remove some amount of potassium existing in this inside. Therefore, we can expect that higher catalytic performance. Yes, it works. As you can see, the data in the left-hand side, the titanium containing or zirconia containing catalyst shows much superior activities than this type of catalyst. Again, this is much better than the industrial systems. More important point is that the stability is much higher than this. So now, in this case, I think we overcome the thermal stability problems by introducing the titanium. So from this point of data, we can say that titanium support is not a simple support. The titanium is a possible element in the active phase formations on the surface. In other words, you can tune the support in the sense of surface material synthesis. Actually, I have one company's people in my lab, and then he asked me how to prepare the industrial catalyst more efficiently. They have a lot of problems in their preparation process. Then, based on my research data, I suggest them one simple preparation process. Then they apply this as the process, and they succeeded in making their catalyst better state. So from the basic analysis, basic data can give us more proper knowledge of the catalyst phase formations. They can use this information in their conventional way. I want to skip. I want to go to the second topics. I hope I have time. Yes. Zirconium sulfate species. As I said at the beginning, this catalyst has been developed quite a long time ago, 1979, by Japanese people. The preparation process is shown here. You can first zirconium hydroxide, which can be formed as a precipitate, and then you can add sulfuric acid. Then you can dry it and calcine it at a high temperature. Calcination is very important. Without calcination, you cannot get any solid acidities. This is very important. I have to remind you. XRD phase, very simple. After calcination, the material simply showed the zirconium oxide phase, which is in tetragonal phase. Nothing others, just a simple zirconium oxide. No information about sulfur. Sulfur's information comes from the IR spectrum, but this is really simple information. We cannot guess anything. So therefore, many people has tried to speculate what the active sulfates are. There are so many proposals. They cannot fix what's the truth because the material is ill-defined materials, because the material was prepared by impregration method and high temperature calcinations. Many chemistries going on at the same time on this process. So you cannot avoid the many known factors. Our method is very simple. Just you can prepare the sulfuric acid solutions, and you can add zirconium oxychloride into it, and then you can dissolve it. After 10 minutes, you will get transparent solutions. Very much easy. Then you can start hydrothermal synthesis at 240 degrees Celsius for 72 hours. You can obtain the white solid in the bottom. You can clearly obtain these materials. After repeating the centrifugations to get the solid, the material is over 90%, which is very good. Don't have a loss of zirconia. We conducted the structural analysis by doing such TM analysis, metabolic analysis. So first, we obtained very thin plate in the shape of a hexagonal shape. Then this is very easy to get the hard stem analysis because the material is so thin. The beams comes in and you can collect the clear stem image. In the left-hand side, which is the hard, you can see the hexagonal arrangement of zirconia. Just in the middle, you can see white spot, which is no black spot in the ABF. Sorry, this doesn't work so easily. I cannot point the place of, but you can see the white hexagon and just in the middle. You can also see the white spot, which is a bit weaker than the others. Means zirconia is arranged in a hexagonal manner, but just in the middle, there is sulfur unit. Based on this kind of information, so we conduct risk-power analysis and then confirm the structures. The structure is like this. This is the layer structures. And if you look at the C direct 110 directions, you can see this kind of elemental distributions. You can see the triangle on this, yeah? So the green one is zirconia. The three zirconia is appeared on the top. On top, this one sulfate anion is located with the in this form. So this one is the S-wall bond, and these are totally isolated here, here, and here. You can obtain this such an interesting structure just by simple hydrothermal method. Very interestingly, there is one Japanese guy who started on these materials. He's the first person to obtain these materials. But his analysis is totally wrong. His proposed structure is wrong. But why? Because he just wanted to make coating materials based on zirconia. He didn't care about the catalysis. He just obtained the solid for coating materials. He never reported further, but actually he is the first person who synthesized these materials. But no one in the field of catalysis paid attention to this. Just ignore it for many years. But now we discover these materials. Just to skip this one. Then we start use as a catalyst for testing the solid acidities. Isopropanol dehydration, which is a very simple reaction, but very easy to conduct. Actually, this shows the catalyst shows very high activities, as you can see in the left-hand side. You can see the fresh means no calcinations. Well, it shows activity in this line. After calcination at 500 degrees Celsius or 600 degrees Celsius, the structure is still the same, no change at all. And it shows higher activities, as you can see here, because the surface area is slightly increased. Why surface area increase? During the calcination in an inert gas atmosphere, some water remain. After the hydrothermal synthesis, some water incorporated into layer space. During the calcination, water comes out. By this process, some layer stacking is going to be expanded, and then it doesn't recover to the original state. So therefore, the surface becomes enhanced. The basic structure is the same, but simply the surface area increased. Therefore, the activity is so high. Just comparisons with the other typical solid acid catalysts. There are many, but as you can see here, it's easy to see that the sample we prepared in this process is much higher than other typical solid acid catalysts. Which is so remarkable. Even the materials we prepare is much superior to the conventionally prepared sulfated zirconia. Again, I have to emphasize that the conventional material has to be calcined at high temperature. But here in our case, we don't need it. Just put this material into the reaction, then you can expect acidic catalysis. That kind of thing has to be done more in any cases. Like, this catalyst is also good for normal butane oxidations, as you can see, but it shows some deactivation during the time, but activity is much superior to the conventional. You can put the platinum onto it, then you can get more. You can get to stabilizations. In this case, we have to throw this hydrogen at the same time. Then the hydrogen can support some active state, because the hydrogen can be activated in the platinum. The activated hydrogen can migrate to some places on the surface. These kind of things happen. Therefore, the catalyst become very stable. But anyway, the material is quite good. So from the simple XRD analysis, we can get very much statistic, how to say, stable structures, which may not be exactly the same as the real catalysis structures. There must be some differences. That's happened in many cases. So we have to know what kind of real structure it is. But we can speculate based on the structure determined, controlled by the structure analysis. Again, the material shows 7 coordinations around zirconia, and SO bond here, and S has 4 coordinations. This is isolated structures. So we can predict the real active site on the basis of this structure determined by the structure analysis. The one thing I have to say here now is that the water is playing as a crucial role in the cause of acid type reactions. Just after the high temperature calcinations, this material shows some activity because some amount of water can be dissolved on the surface. But if you add more water on it, then you can have higher conversions of a new normal butane isomerization reactions. So the water is playing some important role in the course of the these reactions. Very simple analysis. This is the IR spectrum analysis. And these are fresh samples. You can see so sharp, clear, false absorbance of IR. And this one is due to this stretching vibration model SWO. And after calcination, means removal of the water, you can observe the shift of this band from here to here, from this number to this number. At the same time, we observe disappearance of water absorption spectra. After adding of hydrogen again, you observe the same IR band as observed in these fresh samples. So the water is strongly influencing on the state of this species on the surface. There must be some interactions between SO bond and water. That's very simple work. So based on this, of course, we have done a lot of calculation work to support this things, but just briefly, this is the initial state. And after exposing in the water interact with this structure, forming this kind of state. Because the zirconium oxide, zirconium can have 8 coordinations. In this particular case, water absorbed on the zirconium site to form this one. The water interact with its SO bond by such a way. These kind of protons might be responsible for acid catalysis. I don't know why this state is very strong for the reactions. We need to conduct more additional works. But I'm pretty sure that the structure formation can help us to understand more. Again, one classical question is, in a sulfated zirconia is based on tetragonal zirconium oxide. Without formations of zirconium oxide, the catalyst is rubbish. But as far as you obtain the trigonal zirconium oxide, you can obtain the high acid performance. Why tetragonal? The answer is very simple. This material has the same structural surface as tetragonal material have. This 101 surface of tetragonal zirconium oxide is totally the same as 001 surface of our materials. Then our material exposed preferentially because this is a thin plate. Thin plate, this phase is 001. The surface area of 001 plate is very much high compared to the conventional. And again, 001 on the 001 surface, sulfate anions locate totally isolated. That's why the material shows such a high performance for any, not any, but many acid catalyzed reactions. So going to say summary, synthesized catalysts in crystalline form are much superior in most cases. So I will encourage you to synthesize these crystalline materials in your case. There must be some possibilities, although it's not easy to get, but please just get ideas how you can get crystalline solid. Then based on this structure information, you can clearly understand, not clear, but you can get better understanding with the catalysis. And maybe you can tune the catalytic performance by adding some other elements with keeping the original structures. This is also the possible way to do it. And the fourth, if you can apply more advanced technologies, you might be able to get porous structures resulting in a high surface area. That means you have a higher catalytic performance. But if you can tune the pore side, you can select the molecules. In the case of this, normal butane to isobutane. But if the pore size is reasonably good for these reactions, you can tune some reactions. You can select the molecules, things like this. So there are many possibilities. I just want to skip. Before closing my talk, I would like to thank those people shown in this slide. The zirconium sulfate study was conducted by Dr. Tao, who are now in Nanjing Normal University. And porous materials was studied by Zhang Xinchen in Ningbo University. Satoshi Ishikawa is my former collaborators in Kanagawa University. He is now professor of the Tokyo Institute of associate professor in Tokyo Institute of Technology. And Toru Murayama, he worked with the Professor Haruta in Tokyo Metropolitan University for 3 years. And now he promoted to be a full professor in Hokkaido University quite recently. So I'd like to thank them all, and also thank you for your kind attention.
Thank you very much. It's working. Oh, yeah, it is. Yeah, no, thanks, Wataru. That was excellent. We've got plenty of time for questions, so please. I can't see very well with the lights, so you have to wave your hand right up. Yeah, right in the middle of the back first. Okay, and then I've also got some questions.
Yeah, how many?
I've got 3.
Yeah.
Thanks for a lovely talk. I was just interested if you've ever had any negative results where you've synthesized a highly crystalline material of an inactive phase.
Yeah,
You've
not made something. You wanted to make something and you've not made it.
No, you've made something which you thought might be the active phase, but it isn't. So if you have a mixed system, and then you try to synthesize one component of that as a crystalline phase, have you managed to do that, but then it's had no activity?
Yeah. Well, if you are lucky enough, you can get single phase materials, single step. Of course, you have depends on the preparation stage. You have a different phase, different state of materials, and different compositions. So there are many factors affecting the final state. So, but you have to expect nature's behavior. Yeah, nature always gives us something new if you apply the very correct manner. So, actually, I'm trying to provide you a general procedure of the preparations. But so far, it's not easy. It's not ready yet. Sorry. Yeah.
Thanks.
There's one there. Yeah.
Thank you for the very nice talk. Just a quick question. In your first case study, when you compare the crystal catalyst and the solid catalyst, have you checked or considered the specific activity of the two catalysts? Because the crystal catalyst seems to be more active than the solid one. Well, I'm not sure the specific amount of catalyst.
That's really good questions. Yeah, but probably it's not easy. That's why you have a question. Well, we know the surface amount of vanadium in the case of supported. In the case of porous materials, I expect all vanadium in the structure can involve in the reactions. In that case, I think the turnover number of the vanadium in the porous materials is slightly lower than the supported one. The supported one might have a bit higher, but not bit. I'm pretty not sure, but it might be higher. I don't know the reason why, but in terms of activation energy, that's quite similar. And but pressure dependence is somehow different from the porous one and the conventional. So this is the structure activity looks similar. This looks different, but there are many different factors operating going on inside. Yeah. So I'm sorry, I don't think I have a right answer to your question. It may take a lot of time to that. Yeah.
Very nice lecture. I'm a chemist. So I looked through the substrates. That's also playing a role somewhere in the catalysis. And in the form of an anchoring or a recognition of the active states on your surface. Do you have an idea how the substrate is influencing? Actually, how is the substrate feeling that is the right form that you have?
Substrate interactions.
Yeah.
Oh. I never think like this.
Because in the biochemistry,
Yeah.
for example, in oxidation chemistry, then they have shown that it is essential that you have a sort of a series of water molecules that actually are present in the intimate steps towards the products.
Yeah. But yes, but in my synthesis of a porous type solid catalyst, I expected that there's some influence of the pore structure in the activations of molecules. So because the pore has some charged field, and the catalyst part is located somewhere, so that, for example, methane molecules, right? Methane molecules can easily go through. But if the material has some negative charge or positive charge somewhere on, the methane molecule can be activated in that charge field. Then the excited methane molecules can accept the ability species where you have active oxygen species.
Yeah.
Then the reactions start more easier than the flat surface.
Then I go back to the first question that you had after. Is it not a method that you can disturb actually from starting from your perfect structure towards the situation that you're expecting in the porous system?
Yeah.
And actually find on basis of the negative results what is happening there?
I still do not fully understand this kind of question, but yeah.
Because you have now the privilege of having a real structure that is working perfectly. And maybe there's also the answer by disturbing selectively this your substrate, for example.
Yeah.
The structure, and there from the negative results see what is happening.
But it depends on the size of molecules. Yeah. So in a case of NO ammonia SCl reactions, there is no limitations of molecules because the molecule is so small. everything, these reactants can easily go through
was just going off the, not off the brewery. Often most interesting, but curiosity driven. Yeah. Get to ask my question. If you want to, you go.
Thank you very much for the time. Really enjoyed it. I have a question regarding the crystalline sulfate zirconium oxide. I see that the XRP pattern seems not particularly sharp. I know that the crystallinity probably from the data might be subjected to the instrumental the resolution.
Yeah.
But I wonder if you've done sort of like synchrotron XRP or sort of CNMR or other sort of local structure technique to probe if you've got some presence of amorphous or disordered phase in your material.
Well, I cannot avoid the possibility of the formations of amorphous type materials, but by checking the TEM, for example, we don't see such kind of a state of materials in the field of the analysis. And XRD is almost phase pure. NMR also gives us the phase purities. Therefore, there is not such negative information for the formations of impurity phase. But majority of the material is the crystalline. I don't know, impurity may cause some additional effect in the course of catalysis, but just for the dehydrogenate acid, simple acid catalysis, you don't have to worry too much about it.
Over here.
When working with the zirconium sulfate, the addition of water seems to be very essential to change the properties.
Yes.
Just wondering if you actually try to follow it by solid state NMR by using, for instance, oxygen 17 water to look at the local environment of the water molecule, its coordination and the interactions with the substrates.
Yes. Yes, I'm sure you're right. I actually, yeah, I'm doing right now. Not yeah, just before coming to this conference, I stayed in Germany to give lectures, and I got one audience like you, and she asked me, why don't you collect the NMR? NMR will give us a lot of information about the waters, and you can, you know, so next time, sorry.
Thank you. Last question.
I was just wondering about the stability of materials you obtain. Stability. Stable.
Stable.
Yeah.
Stability. Yeah.
In the first case study where you replaced vanadium with titanium,
Yes.
the material got more stable.
Yes.
So I was just wondering, is it just the higher coordination number of titanium that's doing that, or?
No, the coordination number is the same.
Okay.
Yeah. So I need your answer.
No,
this is a really important thing. I always have a question, why these things happens? What the role of titanium is doing? It's just a simply replacement of the vanadium side with the titanium. The difference is such so simple, yeah? But the material is going to be very stable. So, and I wanted to try to introduce more titanium into this place, but the material refused all kind of trial. Only one titanium is accepted, but two titanium, no. There must be some regulations based on structural formations, some reparations or some band overlapping or something like that. Therefore, we need to characterize these materials more carefully to understand the role of titanium. Yeah.
I'm going to use chairman's privilege because that clock is 2 minutes before that clock.
Which is correct.
I get to ask one thing, but correct time is 2 minutes. Well, yeah, okay. Thank you. Have you ever thought these seem to be very similar to zeolitic type materials?
Yes.
Prepared with it. And in zeolites, you often use a template
Yes.
to make the structure. Have you thought about putting in a template into this to make a bigger structure that you could put more titania into? Because you said you're limited on the amount of titanium you can put in.
Yes.
So if you made a bigger structure,
Yes.
you could probably put more
Yes.
titanium in.
It's so far successful. We have used the template in this synthesis. But the problem is it has to remove template.
Yes, yes.
So we have a variety of solid with different structures, but we can't remove it. Therefore, it's almost useless until because the molecules can go into because the microporous is fully occupied with the template.
But if you choose the template right, you should be able to oxidize it.
Yes, yes. So very recently we have got ideas to removal by the oxidation process. The oxygen molecules doesn't work, but NO or NO2 type molecule is more. Yes. So then it's going to be possible. Yeah.
Well, I'd like to thank you, and with all